Okay, so today I have an experiment to determine the beta value or the hFE value of these NPN BJT transistors. The model type is 2N5551B331. And these transistors are power transistors. So in their spec sheet, they have a rating that they have a max collector emitter voltage of 160, have a max current collector current allowed of 600 milliamperes, and then their gain, the hFE at 5 volts VCE, is at 10 milliamps should be 80 to 250, and 50 milliamps should be more than 80. So first, let's look at how the experiment is set up. So the goal of this experiment is to find the beta, the hFE, by measuring the collector current, the ratio of the collector current to the base current. So how do we find the base current flowing through a resistor, flowing through the base of a BJT transistor? Well, the easiest thing would be to stick a voltmeter across the base resistor and measure the voltage there. But instead of doing that, I'm going to show that the base current can be calculated by just VCC, which is the current, the voltage passed in through the base resistor, minus 0.7, which is the voltage drop across the base base emitter PN junction, divided by the resistor. And the reason why that is well, if we look at without a base resistor, so if I just supplied a base voltage to the base of a BJT transistor, what would be the current through it? The only thing impeding this current is the PN junction from the base to the emitter of the BJT transistor. And the equation that governs a current through a PN junction based on the voltage difference is the Shockley diode equation. And this is, as you can see, an exponential relationship. So what happens is that as we increase the base voltage, should be VBE, the voltage across the PN junction, the current actually does not increase until there's a threshold of 0.7. And this is derived by setting the limits of these constants to expose these constants. And after 0.7, the current sharply increases. So basically, you can model this as the voltage passes 0.7, the equivalent resistance of the PN junction, which is determined by the the voltage divided by the current, is effectively zero. Because as you increase the voltage a little bit, the current spikes really hard. Which means that if we come back to here, if we minus 0.7 from the voltage passed into the base, then the rest of the voltage drop needs to occur across the resistor. And the current is not loading the resistor because it's essentially got zero resistance at that point. So therefore the current through, you can do a KVL, you can do a Kirchhoff current law at this point, which means that whatever current flows through this resistor is the current flowing through the base. And the current flowing through this resistor is therefore this minus 0.7 voltage drop, which is the voltage across here. The difference between these two voltages divided by the base resistor gives you the base current. So now let's look at how we're going to generate the different beta values, well, to match the data sheet. And the way to do that is we're going to pick the base resistors to target a base current, and that base current needs to fall within these specs given by the data sheet. So it needs to generate an IC less than 600 milliamps, and we actually can't target anything close to this. The reason is because the max power is very limiting here. The max power is 600 watts, sorry. It's 600 milliwatts. So if we had 600 milliamps, it means that there's only 1 volt possible across VCE. Otherwise, it would exceed the power limit. So if we're using 5 volts for VCE, we don't have a emitter or a collector resistor. So majority of the voltage drop is going to be across the CE junction. So therefore, in order to get less than 625 milliwatts, we want to target a much lower current because it needs to be multiplied by 5. So here I've selected 3 resistor values, and then from here alone we can already sort of calculate what the IB would be, because it will be VCC minus 0.7 over RB. Okay, so let's do this calculation first. Alright, so the calculated values are 90 milliamps, 215 milliamps, and 430 milliamps, which, if given a multiplication of 100, we should reach about 9, these are microamps, should reach 9 milliamps, 21 milliamps, and 43 milliamps, which should be in the range of this IC. And when multiplied by the voltage 5, it does not exceed the max power as well. Alright, so here I've got the setup, and I've got these 3 resistors. This is the 47K, 20K, and 10K. So let me plug in the 47K first. Going from the power supply to the base. And I'll turn on the voltage source, set at 5.06 volts. And you can see that it's 0.01 amps on the output. So my IC plus IB is 10 milliamps. Next, I want to try something else as well, not just varying the resistance. I want to test multiple transistors of the same batch to see if there's any differences. What's the consistency? So let me remove this, and I'll plug in this new one. And then we'll see if we also get a similar value. Let's start. It's not plugged in properly. This one is plugging into a different socket. Should be this one. Alright, let's see what we get. This is strange. This is the emitter, base. Oh, my bad. It's supposed to be. These breadboard buttons are pretty small. So this is the emitter, this is the base, and this is the collector. So we should do this. Alright, let's see. There you go. You got 10 amps, 10 milliamps. So both of them are pretty consistent. This one sometimes goes to 11, but it's still almost the same. Next, let's go with the 20K. Let's go with the 20K, and we get 26 milliamps. just to test our sanity, let's check the voltage on the input of these terminals and see if we actually get the expected values. So I'm going to use my voltmeter. So we should see about 5 volts drop across the input of the base resistor and the ground. So here we see it's 4.97 volts on the voltmeter across here. So that's very good. Next, let's test the base emitter junction, which we expect to see 0.7 volts, and we get 0.6678, which is acceptable, close enough. And yep, let's test it with the other transistor now. Make sure that they're not that different. Again, we get 26 milliamps. It's very consistent on the same batch. So this is apparently what you find with transistors of the same batch, is they have a similar hFE, but on the same brand of transistors on different batches can have wildly different hFEs. Next, let's test out the last resistor, the 10K. All right. And that's 54 milliamps. 56 milliamperes. Let's test it on the other transistor. And 54, 55. The gain actually changes when the transistor heats up a little bit, but as you can see, it's sort of hovering around 54 to 56. So we'll just make that the same, 56 milliamps. All right, now from this, we should be able to calculate the beta values by first getting the IC, which is just these values minus the IB, and this is basically negligible compared to this because it's such a big gain. So we can straight up just divide it and we'll get an approximate value. So I'll do that and come back. All right, so the calculated values are as follows. At 10 milliamps IC, we get 111 gain. At 26 milliamps, we get 120, and at 56, we get 130, which is all within the acceptable values for the manufacturer. So this transistor is doing what it's saying it's doing, but as you can see, the beta varies when you have a different current. And this is as expected of a NPN transistor, which is why when actually using the NPN transistor, because the gain is so different, you cannot use the base voltage alone to determine the collector current. You have to use something called emitter degeneration, which adds a resistor onto the collector. And that's a demonstration I'm going to make another video for.